So we're making a RootKit. Before I start the first video, which is going to be the basics of just executing shellcode and whatever, I want to talk a bit about this series that we're going to make. It's going to be a multiple video series where we go step by step in different techniques to evade EDRs, different antivirus solutions, make our malware more untraceable, write our own shellcode to have it less detectable on network traffic, doing stuff like socket stealing, and also doing some kernel stuff, maybe writing a custom like kernel driver. I'm not really sure yet, but I've never written a rootkit before. I know about the concepts in theory, but yeah, this is more like of a documentation for me, so I can, prove that I actually know what I'm doing. Yeah, so one more thing. I want to open up a Discord or something like that. So if you have like questions and stuff, you can join the Discord and ask me personal questions, because besides the series that I'm going to make, I really don't know what I should make videos on. So if I could like make videos about the questions that you guys ask in the Discord, then that'd be great. Yeah, so let's move over to the desktop. So the first thing you have to understand, or basically I'm guessing that you are a not still a script kiddie, but a person that has dabbled with a little bit of Python, maybe a bunch of batch scripts, a little bit of PowerShell, to kind of make malware droppers. So essentially just malware that downloads other malware and then hides it in the startup folder, and like have dabbled with a little bit of persistence and whatever, but you don't really know how to make the base executable that then actually gets a callback to your C2. Beginners usually use stuff like Metasploit, right? MSF Venom to generate exe payloads that they can just drop on like CTF boxes. But those obviously are heavily signatured, and you can't really use those in real world scenarios. So you have to learn how to make your own, right? And that's basically what this is going to be. This is not going to be the, this is the initial payload that the victim is going to click, and then that's going to download that, and that's going to download that, and that's going to hide that in this directory. It's not going to be a lot of that. It's going to be more of the final executable having the shellcode executed, or we're going to do some shellcode injection and stuff. And yeah, so it's going to be more of that. So if you're a person that has like a little bit of Python experience, a little bit of batch and PowerShell experience, this is perfect for you. It's a perfect starting point. So what you have to understand is how memory works, because we want to basically tell the computer to give us access to it, right? First of all, you have to understand what shellcode is. Shellcode is basically just instructions that we give the computer to tell him, hey, give us access to the computer. It's basically the reverse shell that you code, but instead of it being actual code that you can read, like with Python, for example, it's going to be hex bytes, and that's just the hex representation of assembly. And assembly, you might have heard of that, is just the translated, or not translated. It's also not, I'm not that good with computers, right? Like I only code the stuff and then it works somehow. I don't really know the deep low level stuff, but assembly is kind of like a lower level programming language that computers can directly, it's instructions that your CPU essentially executes, right? Like Python eventually gets translated to assembly, so your CPU understands it. Yeah, so we have shellcode and we want that to execute. And you can generate your shellcode from MSF Venom, just like you can generate the exe payload. You can just generate a shellcode blob and we want to give that to the computer and tell it, yo, execute that, so we get a callback on our interpreter session. That's what shellcode is. That's the instructions. I like to use the analogy of the house with a butler and his assistants while explaining memory of a computer, usually. So imagine your computer as a house, right? A big villa, a big noble villa. And in the villa, there's obviously butlers, right? And those butlers are the different programs that we have. We can use programs and processes interchangeably. They're kind of the same thing. There's like small differences. A program has multiple processes, but essentially they do the same thing. So a butler is a program or a process that has multiple threads. So a butler has multiple assistants, which the butler tells the assistants what to do. Like let's say the task of the program is to clean the house. There's one butler in charge of cleaning the house. There are multiple tasks you have to do when cleaning the house. You have to mop the floors. You have to, you have to like wash the toilet. I don't know. You have to make the bed. Like there's multiple things that you have to do, right? So the butler essentially has multiple assistants for each task they have to do. Just like your browser, for example, on your computer has multiple threads within each tab to have different instructions executed, like the movement of your mouse and waiting for a click to happen and then handling that click. Those are all different instructions, and most of the time those have different threads that are waiting for those actions to happen to then carry out instructions based on those actions. So the structure of like Windows processes is there's a process, now there's a program, has multiple processes. Like for example, Firefox itself is the program. It has multiple tabs, which each of them is a new process, which is why it takes up so much RAM. And then each process has multiple threads that do multiple things. So it's kind of like that hierarchy. So let's draw that right here. We have the process, the program, my bad, has multiple processes, and each process has one or multiple threads that then actually carry out those instructions, right? So what we need to do if we want to give the butler a new instruction, if we write a program and we want to tell it what to do, is we go up to the butler, right? Let's draw a little stick man, that's us. We go to the butler and we tell him, hey, we want you to carry out some instructions. And basically what we're doing in the programming language is we're allocating memory, because a program could be full already, right? The reserved memory for that program that it has by default could be full already. So and that's how I understand it, right? I do not know if that's true or not, but it's simple to understand it that way. So it might have a lot of memory that's already being used with instructions in it that is going to carry out. So the butler might already be pretty busy. What we need to do is, hey, look, we got to tell them, hey, look, we want to execute new instructions. So that's called allocating memory, which basically is like reserving memory or saying, hey, we want to execute new instructions, so make sure that you have place for somewhere for us to put those instructions into. So then the program makes that space and says, hey, yeah, great, of course. And it reserves us a page of memory and gives us the address. So that now we can, and you can think of this page of memory as a table where every assistant just goes to its assigned table and takes off the instructions off the table and then just goes and executes it. So then we say, oh, perfect. We know where to put our instructions. Now we actually put our instructions in there. And then once the instructions are where they're supposed to be, we tell an assistant, hey, look, there are instructions for you, go execute those instructions. That's basically how it works. Super bad explanation, right? But that's how I kind of wrapped my head around it when I first learned about it. So what we need to do in computer terms, like the official terms, is allocate memory, then write into that allocated space, and then we have to create a thread to execute that region of memory. Yeah, so let's do that right now. My fucking camera died. Okay, I got this blob of shellcode right here, which, I mean, you can see this is not code, right? This right here is code that we can read. This right here, that's just numbers and OX and whatever that is. That's the hex representation of assembly that I talked about. Each byte represents each sequence of bytes represents an instruction that the CPU can execute. But I don't want you to just see the finished code. I want you to follow along with me and actually make a shellcode loader yourself. So let's open up a new project. Let's make that a console app. Wait. And let's this video. Excuse me for the long load time, right? But if you have such a low attention span that you can't, wait for 5 seconds for my computer to load my stuff, then you shouldn't be watching this anyway. Okay. So let me get rid of all these comments. Right. Now, how we interact with the operating system or the hardware essentially, because we're interacting with the hardware when doing memory stuff, is there's an API for put there by Microsoft for us developers to use, which has legitimate uses, don't get me wrong, but a lot of it is just used for malware. Yeah, because it's so convenient, right? Right, so first thing we need to do, or what I want to do, I don't want to put it in the main function, right? You should know basic programming. I'm going to make an exec function, which is going to have the shellcode, which I'm going to put in the description, by the way. You can just copy and paste it, and don't worry, it's not going to be harmful. The only thing it does is open up Notepad. Why is that not? Dude. Okay, bro. Alright, because I unplugged my keyboard. My fault, guys. I'm gonna have to use this. Go over here. There we go. Okay, here we got the shellcode blob. This is the instructions to basically execute Notepad, which we're going to tell the CPU to do. So, what did we talk about? Did we have to do first? We have to allocate memory. How do we do that? I'm going to tell you how, but I'm also going to tell you how you can research that stuff, because I just told you that, there's the Windows API that we're going to use. So let's look at the Windows API documentation. Allocate memory Windows. There we go, virtual alloc function. So we know the function is called virtual alloc. Virtual alloc. and we can put a comma right here to see the arguments. And we can allocate memory at a specific address, which is not going to be important right now. So we can just keep that as null. By the way, I can just look at the documentation as well. And all of the parameters are going to be explained right here. You see the starting address of the region to allocate, right? We can specify that if you want, but if it's null, the system just gives us a random address. Then the size, like it's pretty obvious how much space do we need. Then the allocation type, memcommit and memreserve, we're going to use both. It's not that, important to know what that is right now. And then the protection of the page that we're going to have, which I'm going to talk about why that matters as well. Now, the size is going to be the size of our buffer, because we want to put our shellcode into memory, right? And the allocation type, as just said that, mem commit and mem reserve. And then the protection type, we're just going to keep it simple. We're going to use page execute read write, and this is basically what you can do with that page of memory. If you set the protection type to page read write, then you can read and write into that memory, but you cannot execute that chunk of memory. If you set it to page execute read, you can execute and read the memory. Pretty simple, right? This right here gets flagged by antivirus like pretty much all of the time. And it depends on what shellcode you use. Some shellcodes, in my experience, interpreted shellcodes needs you to have page execute read write, which is why I don't really use it. Which is why we're going to make our own as well. Because if the shellcode modifies itself, it's going to have all of the permissions that it needs, right? But because this has like no legitimate uses to first write into memory and then execute something and to also read it, it's pretty suspicious, because a lot of people do that to execute malware. There's ways around that, like we can use virtual protect to at the allocation stage first set it to read write, and then write into it, then protect it, like change the permissions to execute read. So we never had it to set to page execute read write, but we can still write into memory and also execute it. But we're going to do that in another video. We're going to keep it simple right now. Okay, we're going to allocate the memory. So we're going to have the space in memory to put our shellcode in. And I'm just going to, can I please get the autocomplete? There we go. And wait, the return type is specified here as well. Where is it? Return value. The return value is the base address of the allocated region of the pages. And so let's save that in a variable, lp void address is equal to virtual alloc, because the return type is going to return an pointer to our page of memory. And then if that value is equal to null, I think it was, right? If the function fails, the return value is null. So if it is null, then we return 1. And before that, we're going to std, we're going to just print f. Failed to allocate memory. And then we're going to return. Why is he screaming at me? Am I stupid? Oh, right, the return needs a semicolon. You can see how inexperienced I am. So after getting our space in memory, we're going to have to put the shellcode into memory. And how are we going to do that? Let's Google write memory windows, and the function is called write process memory. Here we go, first result. I mean, you can see this stuff is not hard. Like, I was overwhelmed at first when I first started to learn that stuff, because I thought, oh, it's so scary to work with like low level stuff. But it's all like super well documented, and you can just find this stuff online pretty easily. So let's see. Here we go. Write process memory. You can see the arguments like this, but let's check what they actually mean. H process, a handle to the process of the memory to be modified, right? Because we can also change the memory of other processes, right? How do we get the handle of our process that we currently use? Well, let's Google get own process handle, get current process. So let's handle hproc get current process. Does this have arguments? Nope. And now we can supply that as our first argument, because we want our own process to be modified, right? And that changes based on what kind of stuff we do, but for simplicity we're going to do that right now. Now, what should we execute? And we're going to execute obviously the instructions that we put into the memory. And where is that? Well, we got the address for that, so let's tell it go there and take those instructions and then execute them. Well, executing is going to be another function, but put those instructions right where we got the free space. So we got the address, where to put it. Now, what do we even want to put in there? And we're going to have that be our buffer. Oh wait, all of these need to be pointers, no? Pointer to our, no, because that's already a pointer, okay. Now we're going to, my camera keeps fucking dying, bro. Now we're going to look at how much it should write into memory, and we could either put this number right here, but you know, it's pretty good practice to just use size of. So again, size of buff. Then write process memory returns something. Here you can see out, so it returns that value, which basically tells you, like this parameter basically tells you how many bytes it actually wrote. And that's great for debugging, but we don't really need it, so we can just leave it as null. Yeah, so that's it. What's the return value? If the function fails, return value is 0. So let's int, right? Because if the return value is 0, and let's add another check to see if that worked or not. It was equal to 0. Printf failed to write memory, write into memory, and we're also going to return. Right, now next step, we have allocated the memory and we have written into the allocated space. Now we want to execute it, and we can, by the way, compile this and see if it works. Oh wait, we need to call the function as well. You can just press Ctrl-Shift-B to compile it, and the window somehow spawned over here. I don't know why. Is that the, yeah. So you can see here the debugging info. Right, it doesn't return a value if everything succeeds, so return 0. There we go, it's successfully compiled. Let's copy the path. And let's execute the program. And it printed hello world because that's the default thing. But if we succeed all of those, let's just printf success. Or we could also just print out the address or the shellcode itself. But you know, if it doesn't correspond to those values, we know it worked because it would correspond to those values if one of the functions failed. So let's compile that again. There we go, success. Right, so everything's working. Now, last step is to create a thread, which, I mean, we saw right here, we have to call a butler to tell it to execute the region of memory, which the assistant of the butler. Yeah, I get my analogies wrong, but essentially we have to create a thread, right? How do we do that? Well, let's Google create thread Windows function. Boom, we got a function. There we go, create thread. So and it returns a handle, as we can see. Let's do handle h thread is equal to create thread. And now let's look at the parameters. The parameter LP thread attributes is going to be a pointer to the security attribute structure, blah 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 blah. If it is null, the threads gets a default security descriptor, so we can leave it as null. It's not important. The initial stack size in bytes, the system rounds this value to the nearest page. If the parameter is 0, the new thread uses the default size for the executable. So we have to look at what size the shellcode is that it's going to execute, which is going to be size of, oh no, never mind. Yeah, I'm getting my stuff wrong. Yeah, we can just leave that at 0. So let's put that at 0. Now, because now we give it the start address, and then yeah. So now we need a pointer to the start address, which we already have, right? The address that we also use to write. So we have the address, and that needs to be LP thread. What is that? LP thread start routine. I thought it was. Oh, because it's a different type. It's not the LP void, right? But we can just typecast that. Right? Yeah, that's what we do. So instead of, because it has to be an LP thread start routine, let's just typecast that. Start routine. And by all means, like, again, I want to highlight, I'm not an expert. I'm just a random kid that, you know, figured this stuff out on his own. So I get a lot of stuff wrong because this hasn't been taught in my school. I'm going to uni. I'm going to, like, learn this stuff in depth, right? And then I'm going to get my stuff right. But for now, I mean, if it works, like it works, right? Don't fix it if it ain't broke. So we have the start address. We can give it a parameter. We can give the thread a variable to work with, but that's optional, so we can just leave that as null. DW creation flags. We can create it suspended, which we're going to do when doing more kind of the evasion stuff, which means that it waits for someone to basically start that thread again. So it gets created and it knows what instructions to execute, but it waits for someone to say, hey, okay, now go execute. We're not going to do that. I think you can also just leave that at null if I'm not incorrect. Or is that like, here we go, 0. Basically it runs immediately, right? That's what we want. And it gives us a thread ID, which we can also use to, interact with it. But if it's null, we do not need it. We just need it to execute. And there we go. We have the create thread. Now, one more thing which I've had with this shellcode is it takes some time, and we need to wait for that thread to finish executing before returning and exiting the process, because otherwise our shellcode won't execute. That's pretty simple. We can just do wait for single object, have the handle to the thread, and then just wait infinite. Damn, why is that so big? Infinite. And then just wait. Infinite basically means wait till it's done executing. So, quick recap. What do? We declare a buffer with our shellcode. We get a space in memory to put our shellcode in. Then we put the shellcode in that memory. Then we tell the assistant to, get those instructions and execute them. And then we wait for him to finish. And then we say, hey, we did it. And then we exit. So let's try that. Right, because I've not got it. One more thing that you have to consider is this is 32-bit shellcode, which basically, I don't really know the history behind it, but 64-bit, there's two different types of shellcode. There's 32-bit and 64-bit, and that is basically because back then there have been different processors, right? And different CPUs that could only handle so much memory to do instructions, right? And as time moves on, obviously we improve as humanity, and we developed not a new system, but like we developed newer CPUs that support newer set of instructions, which are faster and which basically are more efficient. And that's basically the kind of difference between 32-bit and 64-bit shellcode. This shellcode is in 32-bit, so we obviously have to set the program to be 32-bit shellcode, to be in 32-bit as well. So the computer actually knows, because the modern processor, most processors are compatible with both types, right? But we have to have that executable be the type of the shellcode that we actually want to execute. Also, when we do shellcode injection later, we have to pick a 32-bit process if we have 32-bit shellcode, or vice versa, right? So we compile that again, this time as 32-bit shellcode, and this is going to put it in a different path. So we're going to copy that again. And we're going to clear that. And hey, let's go. The notepad spawned on my different monitor, but hey, woohoo! Yeah, you can do that again because now it's going to spawn here. Fucking hell, bro. Yay! Right? One more time. Woohoo! So that's basically how you execute instructions on Windows, or also on Linux, right? But you wouldn't use the Windows API on Linux, obviously. Yeah, you can put any shellcode you want in here. I mean, you can generate shellcode from Meterpreter, and actually this is Meterpreter shellcode, just for doing a simple exec of the calculator. It's the Windows exec payload. But you could just do a Meterpreter reverse shell and it would work. It would give you a callback. Yeah, this obviously gets caught by Defender because this is pretty obvious, but we need to understand the basics before we can move on to make some cool stuff and evade stupid bitches like the Windows Defender, right? Yeah, that's pretty much it. Please join the Discord, please ask me some questions, because other than that, I have no idea what to make videos on. Like, I have found a few bugs, I found a few CVEs, I could make videos on those, like telling you how to find your first CVE, or an example of what my first CVE looked like. I could do that, which by the way, it's still out there, like it hasn't been fixed. They know about it, but they just didn't care. It's always the same. Yeah, I mean, I hope you learned something. I hope this wasn't a complete waste of your time. See ya.